Hi everyone. This module is MSc Chemistry 4th semester, Inorganic Chemistry Unit 7. In this module, I am going to discuss with nuclear magnetic resonance spectroscopy. This nuclear magnetic resonance spectroscopy is one of the very important tools to determine the new synthesized compounds. In this module, I am going to discuss with what is NMR spectroscopy, instrumentations of NMR spectroscopy, practical limitations to metal NMR spectroscopy, favorable properties, chemical safe, chemically equivalent point, spin-spin coupling, how to interpret the spectra, proton coupling, phosphorus proton coupling, fluorine NMR spectroscopy, boron NMR spectroscopy, spin-spin coupling between that boron and nitrogen, and lead, platinum, palladium, NMR spectroscopy of organometallic compounds, and summarize that. Here NMR stands for nuclear magnetic resonance. NMR stands for nuclear magnetic resonance spectroscopy. Takes advantage of magnetic properties of certain nuclei and other records absorption energy between quantized nuclear energy levels. In NMR experiment, the spectrometer is tuned to the frequency of particular nucleus and spectrum reveals such nuclei in the molecule being investigated. It is very powerful technique, the closest analogy being a powerful microscope that allows the chemist to see the structures of the molecules in the solution. Actually, the NMR experiment does not directly show how all the atoms are connected. Accordingly, it is set up to chemist to take the information provided by NMR spectra to build a model of the molecule. The analysis of NMR spectra is very much like putting a puzzle together. The structure of the molecule will be known when all of the pieces fit together. Okay, the multinuclear NMR spectroscopy is the name given to study of NMR active nuclei of elements other than protons, carbon 13, nitrogen 15, boron, fluorine, phosphorus, selenium, stannous, mercury, etc. The nuclei have spin number I, that is denoted by A of or 1 by 2 or NMR active. The second most sensitive nucleus for NMR is 19 fluorine. In addition to charge and mass, which all nuclei have the various nuclei, also possess a properties called nuclear spin, which means they were spinning. Since nuclei have a charge, they generate a magnetic field with an associated magnetic moment. NMR is possible owing to the magnetic properties of certain nuclei. The very useful empirical rules relating to that mass number, atomic number, nuclear spin, quantum number, they mentioned in that paper. If mass number is even, atomic number is even, that nuclear spin is 0. If mass number is odd, nuclear number means atomic number is even or odd. What we are getting here? 1 by 2, 3 by 2, 5 by 2. When this mass number is even, atomic number is odd, what we are getting? That nuclear spin quantum number is 1, 2, 3. The NMR depends only on existence of a nuclear spin. Nuclei with I is equal to 0 have no NMR spectrum. For example, carbon 12, oxygen 16, oxygen 18. The most important class of nuclei are those with I is equal to of or NMR active and give sharp NMR spectrum. Nuclei with I is greater than half. For example, boron 11, nitrogen 14 have quadrupole moments, a non-spherical distribution of nuclear charge, which results in broad absorption lines and makes observations of spectra more difficult. The quadrupole moment can even affect the line shape of neighboring nuclei. For example, resonance of protons bonded to nitrogen or boron atoms are generally drawn in proton NMR spectra. We shall thus be primarily concerned with nuclei where I is half, but the effect that quadrupolar nuclei can have on the NMR spectra of I is equal to half nuclei should be remembered. Yes, some of the isotopes with spin are mentioned in that table too. This is isotopes that hydrogen exists in different isotopes: proton, protium, deuterium, tritium, carbon 12, 13, 14, nitrogen 14, 15, fluorine, silicon, phosphorus, iron, selenium, yttrium, rhodium, silver, cadmium, stannous, tellurium, xenon, cameron, tungsten, osmium, platinum, mercury, thallium, lead. These are all what here different isotopes exist in that nature. The percentage of natural abundance are mentioned in that table. What are the practical limitations to metal NMR spectroscopy? The NMR spectroscopy of metal is a very much unfavorable. This is because of smaller number of nuclei with favorable nuclear properties for high resolution NMR. As the technology evolves, more nuclei bond types are being brought into the spectroscopist nest. The NMR properties of various nuclei are mentioned here. These are all non-metals. The percentage of abundance are mentioned here. This is the nuclear spin. This is the magnetogeneric ratio. This is quadrupole moment. This is relative receptivity. We consider that metalloids like boron, silicon, germanium, osmium, antimony, tellurium, these are all metalloids. Means these elements exist both metal as well as non-metals. We consider that metals like alkali metals, alkaline earth metals and transition metals are tabulated here. What are favorable properties for high resolution nuclear magnetic resonance spectroscopy? The spin quantum number is half or greater than half, a relatively small value of the nuclear electric quadrupole moment, a large value of I to minimize quadrupolar broadening. Also necessary are a sufficient large natural abundance, magnetogeneric ratio. Effectively, the ratio of the magnetic moment to the spin quantum number, that is what magnetogeneric ratio, to which the nuclear magnetic resonance frequency is proportional. The intrinsic NMR receptivity, which is measure of the intensity of signals increases, the large values of high are more favorable by a factors of 33 from I is equal to plus of to 9 by 2. The transition metals nuclei with natural abundance below 5% that may be usefully studied with enrichment or iron, nickel, zinc, possibly. The spin I is equal to half nuclei with low frequency values of further problems to see to slow relaxation. This is the NMR experiment. A sample is placed in a strong magnetic field B0. Since they spin off the magnetic nuclei are quantized, they can have only certain well-defined values. If we have nuclei with I is equal to half, the spins can orient only in two directions, either with M1 is equal to plus of alpha or against M1 is equal to minus of beta, the applied field. The NMR transition are allowed for causes where delta Mi is equal to plus or minus 1. There is an energy difference delta E between two states, and this is given by delta E is equal to H mu is equal to H by 2 pi mu beta naught, or mu is equal to 1 by 2 pi mu beta naught. This is applied field, this is nuclear state spin. This is the energy between alpha and beta. Here that is what delta E, that is equal to what H mu. Where it is Planck's constant, mu is gyromagnetic ratio, and we consider beta naught is applied magnetic field. The above equation is very important since it shows that delta E depends only on mu and B naught. The gyromagnetic ratio is an intrinsic property of the magnetic nucleus. Therefore, each type of nucleus has a distinct characteristics value of mu. This is what differences in resonance frequency of the nucleus under same B naught. This is B naught expressed in that unit Tesla. This is 2.35. This is proton. This is carbon 13, boron 13, fluorine 19, and phosphorus 31. Next, a very important concept is chemical shift. Chemical shift means the variation of resonance frequency with chemical environment is termed as the chemical shift. The variation of the resonance frequency with chemical environment is termed as the chemical shift. Here the actual field B naught felt by the nucleus and thus less than beta naught, and the ability to electrons to alter the field felt at the nucleus can be expressed sigma. The shielding effect is written as B local. Here B naught into 1 minus sigma. These are all the expressions to calculate the chemical shift values in the different ratios. The more modern NMR spectrophotometer generates spectra by varying frequency while keeping the magnetic field strength B naught constant. Nevertheless, the upfield and downfield terminology remains in common use. Unfortunately, the result in the confusing situation that delta is positive in the direction field. This is what? High shielding, low frequency up to field. This is tetramethylsilane. This is low field. Low shielding means high frequency downfield. The one important consequences of chemical shift is that each chemically different type of NMR active nucleus in a molecule will give rise to its own signal since an NMR spectrum. The nuclei are thus referred to as chemically equivalent or chemically inequivalent in determining how many signals will be absorbed in an NMR spectrum. For example, both CH3Cl and CH2Cl2 provide one resonance each in the proton NMR spectrum in below figure. This is mirrors in the plane of the phase renders. This is the threefold rotation axis demonstrates HA is equal to HP is equal to HC. Just to consider here some of the examples of this ether group. The CH2 groups are equivalent and the CH3 groups are equivalent to signals in either the protons or carbon 13 NMR spectra. Here the CH3 groups are inequivalent, 3 signals in either the proton or C13 NMR spectra. Here the CH2 groups are inequivalent, 3 signals in either the proton or C13 NMR spectra. Here we consider there are two distinct set of CH3 groups, 2 signals in either the proton or C13 NMR spectra. This is sulfur hexafluoride is a highly symmetrical octahedral molecule. It gives only one signal in fluorine NMR spectrum. The axial and equatorial fluorines are chemically inequivalent, hence there are 2 signals are seen in the fluorine NMR spectrum. The apical fluorine is chemically distinct from the 4-fluorine in the square base, hence 2 signals are seen in fluorine NMR spectrum. We consider the 4-fluorine nuclei in the square base are chemically equivalent, hence 1 signal is seen in fluorine NMR spectrum. These are all some important examples regarding to that NMR spectroscopy. Here what is the integrations? The area under each NMR spectrum peak can be electronically integrated to determine the relative number of nuclei responsible for each peak. The integral of each peak can be provided numerically and is often accompanied by a line that represents the integration graphically. Intensities of signals can be compared within a particular NMR spectrum only. These are all spectrum. If we consider NMR spectrum of this proton, spectrum of this compound, what we are getting here, 3 protons and 1 protons here. At this stage, we appreciate NMR resembles a molecular microscope. For example, at one frequency could see the various protons while carbon, fluorine, phosphorus and even certain metal nuclei could be observed at other frequencies. The next concept is spin-spin coupling. The appearance of resonance may be very different when there are other neighboring magnetic nuclei. The reason for this is that the nucleus under observation will interact with the magnetic spin of the different neighboring nuclei. The simplest case is that of two protons having significantly different chemical shift. Considering chemical shift and integration only, we could represent the spectrum as shown in the figure. Here both the protons have spin half can exist in the plus half and minus half. Now it turns out that the magnetic moment or environment HA is slightly different than HX in the place of state than when it is the minus of state. This can be represented pictorially with arrows representing the two half spin like that. This is correct way. Next we consider this is the protons influencing of neighboring spins is called spin-spin coupling, and nuclear peaks are split into multiplets. As a result, the spectrum between the two peaks is called the coupling constant J, which is expressed in hertz. The magnitude of J measures how strongly the nuclear spin interact with each other. Coupling is normally a through bond interaction. Next we consider the coupling occurs through chemical bond. The magnitude of J normally falls off rapidly as a result of intervening bands decreases. Next we consider this is a molecule of that J1 is not affected by the orientation of the coupled nuclei. So it is generally true that J1 very greater than J2 or J3, but it is not always true that J2 greater than J3. The spin-spin interactions are independent of the strength of the applied field. The spacing between lines at two different field strengths will be the same if it is due to coupling. But but will be proportional to the field strength if it is due to difference in chemical state. These are all typical coupling constant ranges. The coupled nuclei AB in Z star into AB. This is X, this is HH, CH, HB and PC. These are all coupled nuclei. This is the alignment of spin. This is the intensity ratio. Next we consider here from this topic, this is the absence of this coupling, coupled to 1, I is equal to of nucleus, it is doublet. I is equal to 1:2:1, that is what Pascal triangle. According to that Pascal triangle, we have to write that. All these things. In case of when each line at a triplet stage is split again into doublets, the intensity of the overlapping peaks is not identical. A signal of relative intensity, two overlaps with a single signal of intensity 1 to create peak intensity 3. This is what n is equal to 0, n plus 1 is equal to 1, intensity is 1. It is a singlet pattern example of this. The following n value and n plus value is variation, the intensity is also variation, the multiplicity is also variation, the pattern is also variation, etc. Next we will discuss on that phosphorus 31 NMR spectroscopy. The phosphorus NMR spectroscopy is a simple technique that can be used alongside proton NMR to characterize phosphorus containing compound. When used on its own, the biggest difference from proton NMR is that there is no need to utilize deuterated solvents. This advantage leads to many different applications of proton, phosphorus NMR, such as assaying, purity and monitoring reactions. Phosphorus 31 nuclear magnetic resonance is conceptually the same as proton. The phosphorus nucleus is useful in NMR spectroscopy due to its relatively high gyromagnetic ratio. For comparison, the gyromagnetic ratio of proton and carbon are they give. Furthermore, phosphorus has 100% natural abundance. Like proton nucleus, the phosphorus nucleus has a similar spin of 1/2, which makes the spectra relative to interpret. The phosphorus 31 NMR is an excellent technique for studying Phosphorus containing compounds such as organic compounds and metal coordination complexes. Next, what is the difference between the proton and phosphorus in NMR spectroscopy? There are certain significant differences between proton and phosphorus. The proton NMR spectra is referred to tetramethylsilane. The chemical shift in phosphorus reported the phosphoric acid, which is used as an external standard due to its reactivity. The tetramethyl phosphate is also used since, unlike phosphoric acid, its shift delta is equal to 140 ppm. Is not dependent on the concentrations or proton. The chemical shift in phosphorus proton commonly depend on the concentrations of the sample. The solvent used, the presence of other compounds. This is because the external standard does not take into about the bulk properties of fluorine. How to interpretations of this phosphorus? As in proton NMR, phosphorus signals occurs at different frequencies depending on the electron environment of each phosphorus nucleus. In this session, we will study a few examples phosphorus containing with various chemical shift and phosphorus. These are all representations of this what? Mass spectroscopy. Next, proton phosphorus coupling. Consider the structures of dynamic dimethyl phosphonate shown in figure 4 as the phosphorus nucleus is coupled to a hydrogen nucleus bound directly to it. We consider this diagram of this. The phosphorus nucleus coupled to a hydrogen bond directly into it. This coupling to fluorine. The fluorine NMR is very similar to phosphorus NMR. That fluorine 19 has a spin half and is also 100% abundant isotope. As a result, fluorine NMR is a great technique for fluorine containing compounds and also allow observance of phosphorus fluorine bonds. The coupled phosphorus 31 and fluorine 19 NMR spectra of epoxy base triuranomethyl phosphate PCH3 or oxalates are shown in that figure. It is worth noting the splitting due to JPCF electrolyte. What are the phosphorus NMR applications? The phosphorus NMR spectroscopy gives rise to a single sharp peaks that facilitate differentiating phosphorus containing species, such as starting material from products. For this reason, 31 phosphorus containing species. Quick and simple techniques for assaying sample purity, behavior. However, the chelation phosphorus 31 spectrum does not necessarily suggest to pure compound. These are all some monitoring reactions. The reaction can be followed by phosphorus NMR by simply taking a liquid from the reaction mixture and adding it into an NMR tube, filtering as needed. We consider that some of the peaks with respect to that proton as well as that phosphorus. This is reaction time. This is reaction time 1 hour, reaction time 2 hours. What happened here? The phosphorus NMR spectrum recorded at different reaction times. And there is no need for deuterated solvent. With samples simplifies samples preparation and saves life and time and resources. The phosphorus spectrum is applied, simple, can be analyzed quickly. The corresponding proton NMR spectra for the above reaction would include a number of overlapping peaks, or for the two phosphorus species as well as peaks for both free and bound cyclooctadiene ligand. This is the migrations of two phosphorus signals is used to quantity the amount of epoxide on the non-tube according to mass of epoxide, area of pH3. This is. Now we are going to discuss with some fluorine NMR spectroscopy. It is also similar to what? Proton NMR. After proton and carbon 13, fluorine is the most common nucleus studied by this technique. The fluorine nuclei are spin of nuclei and have a gyromagnetic ratio. This is chemical shift in fluorine 19 NMR. The chemical shift is more sensitive to solvent effect. CFCl3 is generally used as reference in phosphorus NMR. Yes, CFCl3 is inert and alloying is what? You rise to a short singlet. This is the further fluorine NMR spectroscopy are tabulated. The chemical shift values span in wider range from 0 to 900 ppm. The chemical shift are sensitive to electromagnetivity, oxidation state and stereochemistry of the neighboring groups. This is Fluorine spectrum of a mixtures of trifluorotoluene and trifluoroethanol. These also similar to that, protons only. Just you go through that. These are all some examples are mentioned here. F14 spectra of nizol. Bipyramidal, trigonal, bipyramidal in case of phosphorus pentafluoride. The structure phosphorus pentafluoride has been found to be trigonal bipyramidal as shown in the figure. Trigonal bipyramidal polyhedron has two distinct sides, the axial side and the equatorial side. The fluorine NMR spectrum of this compound shows a doublet with the spectrum being the lines corresponding to the coupling constant. Next we consider this is some important applications. In case of boron NMR spectroscopy, the boron 11 chemical shift is very high for two reasons. Because of this, it helps significantly to analyze not only structure but also the center of equilibrium in fluxionol molecules. This B11 can provide additional and significant insight into a distributions of valence band electrons in some fragments of a given molecule and in individual atomic orbitals, which is important for understanding both physical and chemical behavior. The naturally occurring isotopes like boron, NMR active, but the later one is more advantageous for NMR investigation. The success of B11 boron NMR spectroscopy stems from several favorable factors. Because the strong signals of the beta nucleus, boron nucleus, only 80.4% of natural abundance, the resonance at a relatively very high frequency, and the relative sensitivity of the B11 nucleus to difficult perturbations the optimum BH coupling for BH is this one. BH3 is 110 to 130, BH3 90 to 110, BH4 is in between 70 and 80 Hertz and megahertz is in between 5 to 60 Hertz. These are all important, just you note it down. The introductions of higher magnetic field and especially the progress in computational and programming techniques make it possible to obtain the following kinds of information. The number of different types of boron atoms, their mutual ratio between a molecule and a chemical shift of each signal relative to BF3 and OT is equal to ppm, with the positive sign for signals at lower magnetic field and higher frequencies. The number of terminal hydrogens or each boron atom, the position of each substituent and the supplied bridges if present compared to unoccupied and decoupled spectra with proton doubled B11 spectra of equivalent intensity. The number of terminal bridge hydrogens, the number of different carbon atoms in the molecule, their mutual ratio, and the number of hydrogen atoms they bear. The structure of boron networks and the assignment of individual signals, the assignment of all protons, spectra, the presence of boron carbon likes, the presence of fragments with HBCH links, a relatively high J value indicates a connections of the observed boron atom with an adjacent heteroatom such as S. The magnitude of electric field gradients around various beta atoms. These are all some important characteristics of this what? Boron phosphorus spectrum. Why this NMR spectroscopy is not applicable for all the cases? Asymmetrical compounds in which the symmetry causes an insufficient number of cross peaks to be observed, missing cross peak, a reduced number of cross peaks due to overlap ring signals, heteroboranes, since these spectra do not provide information on the links of boron to the heteroatoms. The most informative characteristics of NMR active nucleus is its chemical shift, which reflects its bonding surrounding, coordination, hybridization, bond angles, pi bonding. The charges on individual atoms originating from their positions in the skeleton, inductive and mesomeric effect of the terminal substituents, electronegativity of skeletal heteroatoms, the magnetic anisotropy of neighboring groups, the effect of heavy nuclei ring current. Next, what are the general comments on boron chemical shift? One is that coordination, tri-coordinate boron containing hydrogen and tri-alkyl boranes, substitution of alkyl groups, boraxenes and borohydrates, tetraalkyl boranes. Just we have to just explain regarding that how many peaks are coming from this. What is that? Higher upfield shift and lower downfield shift. Everyone we consider from this. What? Yeah, general comments on that boron chemical shift. Just we consider boron atoms and with some boron related groups. The spin-spin coupling between boron and nitrogen. The unfavorable nuclear magnetic properties of nitrogen isotopes, nitrogen 14 and 15, have not encouraged for spin-spin coupling between boron and nitrogen atom. The rapid quadrupole relaxation of nitrogen is thought to be responsible for the fact that no Z1 can be observed either by boron and nitrogen. The spin-spin coupling between boron and phosphorus. Different situation exists for boron-phosphorus compound. In many cases, the coupling constant J were readily obtained either by boron or phosphorus in a mass spectrum, while the sign Z in organyl phosphine is usually negative and changes to positive when phosphorus becomes tetra-coordinated. Some other NMR active nuclei. A lead is a ubiquitous environmental contaminant, that is we have to find out. The platinum is relatively inert metal and has no natural biological roles, that is also predicted. From this, palladium is a non-essential element for life, means pharmaceutical interest in palladium compound is driven by analogy to anti-tumor complexes as well as that antiviral, antifungal, antimicrobial metallotherapeutics. Palladium as one naturally occurring NMR active isotope. Although it has high natural abundance, this quadrupolar nucleus is characterized by a low sensitivity to detections by NMR. The rhodium has no biological function. Recently, rhodium complexes have been investigations for their possible applications in medicines as anti-tumor, antibacterial and antiparasitic agents. As a monoisotopic species with I is equal to half and a wide chemical shift range, the thorium nucleus is attractive for NMR studies. Unfortunately, the low receptivity, negative magnetozyanic ratio and very long relaxation times are major drawbacks. A recent survey of rhodium NMR spectroscopy has been published here. Next, tungsten is only one quadrupolar NMR active nucleus, but it is characterized by low natural abundance and extremely low receptivity. But despite the interesting biological properties of molybdenum and tungstens, both molybdenum and tungstens, NMR spectroscopy have not often been used to investigate the biological chemistry of these two metals. The tungsten NMR has been to characterize some heteropoly tungstenates tested as anti-HIV agents. What are the important of these proton NMR spectroscopy? Organometallic compounds. We consider in that here, proton spectroscopy is among the extensively used techniques for the characterizations of organometallic compounds. The carbon is containing carbon, metal and halogens. Of particular interest is the applications of proton NMR spectroscopy in the characterization of metal hydride complexes, for which the metal hydride moiety appear at a distinct chemical shift range between 0 to minus 40 ppm to the high field of tetramethylsilane. This upfield shift of the metal hydride moiety is attributed to a shielding by metal d electrons and the extent of upper field shift increases with higher the DN configuration. Chemical shift, peak intensities as well as coupling constant from the through bond coupling between adjacent nuclei, like that of observations of this J. Yes, the phosphorus nuclei is present within the coupling range of a proton nucleus, are often used for the analysis of these compounds. The proton NMR spectroscopy is often successfully employed in studying more complex issues like fluxionality and diastereotopy in organometallic molecules. The paramagnetic organometallic complex shows a large chemical shift. For example, exhibit proton resonances that extended even up to 290 ppm. Now I am going to conclude that NMR spectroscopy, just as in organic chemistry, it is now routine to measure that proton, carbon, often fluorine, phosphorus, NMR spectra of diamagnetic organometallic and coordination compound. Many NMR spectra are measured simply to see if a reaction has taken place, as this approach can sometimes take less than 5 minutes. Having determined that something has happened, the most common reasons for continuing to measure are usually associated with confirmations that a reaction has taken place. By simply counting the signals, deciding how to proceed. The recognition of new or novel structural features via marked changes in nuclear shift. The need for unique proof with sufficient structural resolutions to follow the kinetics or the development of reactions. When a phosphorus atom is present, proton decoupled, phosphorus NMR often represents one of the simplest analytical tools available, as the spectra can be obtained quickly and do not normally contain many lines. These are all important questions. Please go through that. That is most helpful to your semester examinations. Practical limitations to metal NMR, write a note on chemical shift, equivalent nuclei, integration, spin-spin coupling, and write a note on the spin-spin coupling between boron nitrogen, boron phosphorus, the possibilities of NMR spectral study of this lead, platinum, palladium, rhodium, tungsten. What are the importance of these organometallic compounds with the help of this NMR spectroscopy? Thank you.